we're going to be doing a lot of simplifying, and it's going to be both with radicals and exponents. And some things you already know. For example, if I ask you to simplify the square root of 12, we already know that that becomes 2 root 3. But when we have to do like quartic roots, so if I actually ask you to simplify the 4th root of 54, you may be a little bit more hesitant about something like that. Or if I ask you to do the cubed root of 54, you may be a little hesitant. So there's some basic rules we can follow. Number 1, you don't want your exponents to be factors of your index. And what I mean by that is this inside number should not be reducible with this outside number. And the reason that's the case is this is the same thing as 5 to the 2/4. And obviously 2/4 can reduce to a half. So we want to make sure that, if we write this as a fraction, it can't be reduced. Rule number 2, we don't want any fractions as our radicands. So if you have something like this, you're not done. You want to break it into root 1 and root 3. However, this is still not done because we still don't want to have radicals in our denominator, so we would have to do some further work with this. I would say this rule is probably the most useful out of all of them because it really guides you on these exponent rules. You want all of your exponents in your answer to be integers or proper fractions. So for example, if you have 2 to the 5/4, that's not considered simplified because 5/4 is an improper fraction, so that can actually be simplified further. So we want our exponents to be whole numbers or proper fractions. And it's very easy to do. So we're going to go through some examples here and show you how it's done. So in our first problem, I right away pick up on the number 4 and recognize that as a perfect square. So I actually like to change that into 2 squared. And then I still have the 4/3. And the reason that I'm choosing to do this problem this way is if this number is prime, then once you go through your next few steps, you know in your final answer that there's absolutely no further simplification you can do because you've already broken 4 down into 2 squared. So my suggestion would be to convert 4 to 2 squared. Then we can distribute our exponent and get 2 to the 8/3. Now if you look, your exponent is still not proper. In fact, it's worse. Now it's 8/3 instead of 4/3. So what we're going to do is we're going to break this apart. One of our exponent laws says if you are multiplying the same base, you keep the base and add the exponent. So these are equivalent statements. So what I'm doing is I'm going from this format to that format. I'm breaking 8/3 apart. I want to do it in such a way that I have either an integer as my exponent or a proper fraction as my exponent. So for example, if you're like, oh, let's break 8 into 3/3 and 5/3. 3/3 plus 5/3 is 8/3. That is true. However, you can see 5/3 is still not proper. So there's actually a little bit more that we could break it into. We could break it into 6/3 and 2/3, and if you do that, 6/3 is an integer. 2/3 is proper, so both exponents are following rules now. So 6/3 is 2, and 2 squared is 4. Since this problem right here, that part, is not violating any of my rules up here at the top, I'm going to go ahead and write it back as a radical. So it's going to be the cubed root of 2 squared, which is 4. So the answer is 4 cubed root 4. Now number 2 is a little easier because 5 does not break down. However, 7/5 is not okay. So we want to break it into 5 to the 5/5 and 5 to the 2/5. Both exponents are following the exponent rules, so we'll go ahead and write this as 5 to the 1st, and we'll convert that part back into a radical, which is the 5th root of 5 squared, which is just 25. Number 3, I recognize 8 as a perfect cube, so I'm going to convert it to 2 cubed. I'm going to distribute my exponent, And I want to break this up because 15 halves is not proper. So I can break 15 into 14 halves and 1 half so that I get an integer, 2 to the 7th. 2 to the 1 half becomes root 2 again. And you could do 2 to the 7th, it's 128. So since it's not a ridiculously huge number, I'm just going to write it as 128. We'll do another one here. 2 does not break down, but 33 halves is not an integer or a proper fraction, so we're going to need to separate this. I can't do 33 over 2, but I can do 32 over 2, and that will leave me with a 1 over 2. So this becomes 2 to the 16th, which is really big, so I'm just going to leave it as 2 to the 16th. And this converts back into the square root of 2. And then we'll do one more. 5 doesn't break down, but I cannot do 100 divided by 3. However, I can do 99 over 3. So I'll break it into 99 and 1. This gets me 5 to the 33rd. And right here I have the cubed root of 5. So these are going to be very similar. The only difference is they start out as radicals. So for number 6, I don't know what 4 to the 8th is. That's pretty big. So what I'm going to do first is change these all into exponential form. It's always a good idea to use exponents when you have bigger numbers. If I see special numbers, I'm going to change them into their exponential representations. So this would be 2 squared. This would be 2 cubed. And this would be 3 squared. I can then distribute my exponents. And then you notice all of these are not proper or integers, so we're going to need to break all of these up. Can't do 16 divided by 3, but I can do 15 over 3. So 15 and 1. I can break this into 24 and 3. I can break this into 20 and 2. So now all my exponents will either be integers or proper, which is exactly what I want to happen. So 2 to the 5th is going to be 32, and this is going to become the cubed root of 2. This would be 2 to the 6th, which is 64. And then we're going to have the quartic root of 2 cubed, which is 8. 3 to the 4th is 81. And we'll be left with the 5th root of 3 squared, which is 9. So 6, 7, and 8 are relatively simple problems because all of the numbers were special in it. Number 9 is not going to be so simple because 48 is not a special number. It's not a cube, it's not a square. Nothing to the 4th gets you 48, nothing to the 5th. So it's not going to be as simple as these ones, but totally doable still. I'm going to begin the same way. I'm going to write 48 to the 10/6. And then I'm going to actually make this 48 to the 5/3. So just like we want our fractions to be able to reduce, so let's reduce them and make our lives a little easier early on. What some kids try to do is they try to say, well, 5/3 is not proper, so let's make it 3/3 and 2/3. So they're like, well, my exponents are integers are proper, so I'm good. So the answer is 48, the cubed root of 48 squared, whatever that is. Here's the problem. This can still be simplified. And the reason I know that is because 48 breaks down. So I would probably not do it that way unless the numbers are very small and easy to work with. What I would do is make a factor tree and break 48 down. Two things would be, 12 and 4. You can break that to 2 and 2, 6 and 2, 2 and 3. If you circle all your prime numbers, you will see that it takes 4 2's and a 3 to make 48. So 2 to the 4th times 3 is the prime factorization of 48. And the problem did say 48 to the 5/3, so I want to keep the 5/3. And by doing that, I can distribute my exponent. So you can see right now that both of these are not proper, so we're going to have to do some work for both of them. So they are both going to get broken apart. 20/3 can be written as 18 and 2. 5/3 can be written as 3 and 2. So now I have 2 to the 6, which is 64. 2 to the 2/3 and 3 to the 2/3 do not simplify, but I know 3 to the 1st is 3. And I'll be left with this 2 to the 2/3 and 3 to the 2/3. I am allowed to multiply 64 and 3 to make 192. It's time to turn these back into radicals, so we're going to have the cubed root of 2 squared, the cubed root of 3 squared. Since they're both radicands and they're under the same type of root, I can go ahead and multiply them together to make 36. So in my next video, we'll go through some practice problems that involve square roots and perfect cubes, etc. And then I'll teach you another trick.